Hello. Okay, we just have a few people here. Hi, Raya. Hi, Hannah. Hi, Lorelai. Hi, Luai. All right. Okay, looks like we're a little bit low on attendance, which is surprising. Only 4 of you thus far, but there's Adam. Hi, Adam. Hopefully people will still show up and participate. Don't want to lose. Hi, Chris. Don't want to lose steam here. We got 6 of you here, and that's just here we go. Justine, that's 7. Hopefully, some more people show up. So, are we? While we're waiting for people to come into the room, are we doing the food day next week? Justine was working on, I think, mailing us food. Is that right? I caught that correctly. Hi, Micah. Hi, Sammy. Okay, I was just joking. Oh yes, good, good. Picture of sure, but you guys should all make your own picnic. Okay, and Justine, what day are we doing it? As you said, Friday or Thursday? Is that correct? Did we have a vote by the group? No vote yet. Okay. Well, how about the group we have here? Okay. So let's have a quick vote and then we can make a decision based on the people who are actually here. And this decision is Thursday or Friday. Okay. So just, oh, that's like true or false. That's funny. Yeah. Okay. So food day, Thursday or Friday. So just type T or F and then we'll go. Yeah. What do you want? Hi, Octave. Every day is the same in quarantine. Thanks, Sachin, for that positive attitude. Also votes on Thursday. There we go. I think we've got an overwhelming majority for food day on Thursday. So we'll circle that and plan on doing that on Thursday. Okay. Thanks, Justine, for getting that organized. Sam can't connect. Okay, good. So food day on Thursday. Let's get started now on our work in terms of getting ready for the Klausur. Just a reminder, April 20th is the scheduled day for the Klausur. Nothing has changed thus far, but we'll see how it goes, but let's keep preparing. So they gave us a nice little problem. I'm on the 2013 free response here for E&M. They've got a nice circuit with a resistor, a capacitor, a switch, and a power source. And I'll copy it over. So we've got here our power source like that. We've got a point B down here. We have a switch right here that we can go either down to B or up to A. And then the thing connects over here. We've got our capacitor right there. We've got a resistor down here. Oh, there we go. So there we go. So here's the resistor. There we go. There's our circuit. There we go. And we can choose whether to close this circuit down here by moving the switch to B, or we can switch this thing up and close it a different way. Now they start off here by asking us to, it's an uncharged capacitor, and we're going to ask to close the circuit in such a way as to charge the capacitor. And they're asking us to either move the switch to A or move the switch to B. So I think that's pretty straightforward, I hope. So you guys just type in A or B. Let's go. Charge the capacitor. What should we do? All righty, good. You're all coming in with B. So we connect it down here. And if we do that right there, of course, our circuit includes the power source. If we close it to A, there's no power source included in our circuit. And then, of course, we can't charge our capacitor. So B is the correct answer. Check that answer. This was not requiring a justification, just a 50-50 toss up. And then hopefully you didn't need the toss up, by the way. But there we go. So now we are asking, we're going to want to measure the voltage across the capacitor, and we're supposed to draw in how to have the voltmeter. Now, just a reminder for ammeters are connected in series, and voltmeters are connected in parallel to where you want to measure what you want to measure. So in our case, because we want to measure the voltage here, okay, we are going to connect our voltage source. So we do multiple choice. Nah, I think that's silly. So we're going to connect it this way. There we go. Connect it that way to get the voltage or potential difference measured across the capacitor. So they're using the word voltage here, which is like a little bit out of vogue. Now they're saying potential difference, but casually they're actually used that way. So that's part B. We've got credit right now for part A right here. We've got credit for part B. We're doing great. Oh, sorry, A1 and A2, not AII, as we've discussed. Okay, good. So now we're asking to, once we let the capacitor charge for what we call a long time. Again, long time depends on the circuit. It's the equivalent of infinity. And here, and maybe that's just 20 seconds, maybe it's 5 minutes, maybe it's 5 seconds, depends on how the capacitor and resistance are chosen. Then we flip it so that it can discharge. Now, they don't ask that at this point because it seems trivial. But of course, once we've charged it in position B, waited a long time, then we discharge it by flipping the switch to A, because at that point, the circuit is up here. And that circuit, the charges can flow off the capacitor and through the resistor, and at that point, neutralize the capacitor plates. Okay, so we've charged it. Here's the longer side, which is the positive. Shorter side is the negative. So we've built up positive charges here and negative charges over there. And then when we close the switch over to A, then they can discharge, which of course means that the current will be flowing the other direction. So initially the charging process occurs in this direction. This is the initial charging through the C charging direction, and then afterwards in a discharging, this is an added bonus here, discharging, the current's flowing that way at that point. Okay, does that make sense? Okay, IC and ID, charging direction of the current, ID discharging direction of the current. Okay, now either way, we've got this voltmeter here measuring the voltage, and of course we can already picture what the voltage is going to look like, right? The voltage difference, delta V as we call it, versus time t is going to asymptotically approach 0 and have some initial value V0, and of course V0 should be the same value that we had over here, epsilon. Okay, so let's just call it V0. We'll just write that. I think that makes more sense than epsilon just because of the labeling, but otherwise it should look like this. And the equation for the voltage, for the potential difference, should be V0 times e to the minus t divided by RC, where RC is what we call the time constant. RC is known as tau, or the time constant. Good. So here's our equation that we have. We know it's supposed to look like this as it discharges. Okay, that's the way it's charging. And of course, the discharging. The charging process looked like this. Okay, that would make sense as it increased the voltage until it reached V0, whatever value that is. At this point, they're asking for us to graph something against something that's going to give us a straight line. One, and it's going to give us somehow a relationship that depends on something that we can get the time constant for. The time constant is in here, RC. Okay, so looking how this equation is here, this is a little bit more complicated than we did previously, because most of the time when we have this kind of relationship, we can go straight to saying, oh, y equals mx, and like this is the slope and that's x or something like that. But this doesn't work because the slope is of course a constant, so we can just get V0 from that. That's not going to be helpful for us, so that won't work in this case. So we're going to have to use a slightly different approach here and to manipulate this equation in order to get to the point for what we can plot. Okay, so this doesn't work, and instead we got to get this thing out of here, out of the exponent. And as you remember, I hope, is in order to, hi Yanis, in order to get the something out of an exponent, what do you got to do? So to get something out of, hi Sachin, hi, ln would work. Good, Joe. Okay, ln is correct. So we can do the ln here. So we've got here delta V is what we're measuring. Good, and they call it V here. I'm going to take the delta away just for log, shit, I don't like that at all. I'm going to put a delta in there. So just showing you how weird this is. Now, I know we do potential, right? But here, they're using V voltage, which is delta V. So V and delta V are the same thing. That's weird, and it's measured in V. It's super confusing. So that's why we switched to calling potential difference delta V. So I would like to put a delta in there. I'm going to just write it in. So, okay. There we go. So I've changed the problem a little bit to make a delta V. That makes more sense. And it agrees with the way we're making the notation work. And that's good. Okay, good. So now let's take that equation. We're going to take the ln of the whole thing. So we get ln of delta v equals ln. There's a choice that you can make. You can either move the v0 over before. Let's do that, actually. There we go. And then we're going to take ln of this. I think it's going to be easier for you to deal with that. Oh, hang on. We're going to also get tau in there because they said find an equation for tau. Okay, sweet. All right. So, right. So we have ln delta v over v0. Okay. How do you take the logarithm of a fraction? How do you take? Do you guys remember? Subtraction. That's correct. So this is ln v. Whoopsie. Are we still in the picture? We're not. Okay. Maybe. Okay. Should have been better with my space. Sorry about that. So ln delta v minus ln v0. That's just a number. And of course, why did we even do this? Why did we take, yeah, correct, Sammy. So we doing the logarithm of a natural log of e to the minus t over tau. In general, taking the logarithm just pulls the exponent down, and then you multiply by the logarithm of that number. And of course, natural log e is how much? So natural log e is how much? 1, exactly. So all we get here is minus t over tau. Okay, sweet. Now we can resort this a little bit, and we can say ln delta v equals minus 1 over tau times t plus ln v0. Okay, is that too small, or can you read it? All right, it's a little squishy here. Minus 1 over tau t plus okay, is that showing up? I think it is. Okay, good. So here's a relationship. ln delta v equals minus 1 over tau times t plus ln v0. Okay, now let's take a look. That looks scary, but if we remind ourselves as to how we normally write these things, y equals m x plus b. There we go. That means we have a clear association here between the y variable and the x variable and the slope and the y-intercept. So let's just kind of associate them here, make sure we know what we're doing. So y is this one here, y. M is minus 1 over tau. Okay. Green. Whiteboard. Green we had already. Doofus. Hello. Let's do red. So we have here our x variable. And then the last one we got to go here in black would be sheeps. the best black pen I have? Seriously, folks. Okay. Sorry, that's the best black I have. Okay, so this is not going to be working at all. I need a blue or something. Blue, blue, blue. Here. I'm miscapped, but it's blue. That works. Okay, here we go. So we have our things associated with each other. Okay, so y variable is ln delta v. X variable is t. The slope is going to be -1 over tau. And then ln v0 is the y-intercept. Okay, good. Righty, what we're going to do here is we're going to take that equation, write it up here, and then create some room for us. And I'm going to take a picture first to make sure we've got that. Good, got it. So we've got ln delta v equals -1 over tau t plus ln v0. Okay, so and this is y, this is m, this is x, and this is b. Okay, so let's get our graph going. Let's take a look here. First of all, the data we're given, t. Okay, just telling you the range here. Let's go for the t, and then we have delta v, and we're going from 6 to 54. 6, 18, 30, 42, 42, 54. Whoop, whoop, whoop. So there we go. This is in seconds. This is in volts. Okay. Alrighty. Okay, good. Delta V, we've got 252. We have 74. We've got 33. We've got 10. And we have 6. Alrighty, good. Now we're going to take the ln of all these values. ln delta v. Okay, so if we do that, let's see what we got. So 252 ln, we got 5.53. We've got 74 ln, 4.30. We've got 33 ln, we got 3.50. 50. And then we have 10 ln is 2.30. And then we have 6 ln is 1.79. Okay, you guys have been awfully quiet. I just want to make sure you guys are still with me and that's all making sense and I haven't lost you all. Makes sense? Yes. Makes no sense? No. Questions? With you. Good. Awesome. Good. So let's take a look at our values. For time, we're going from 0 to 60. From ln delta v, we're going between 0 and 6. Okay? Good. So we have a graph. And again, they tend to be pretty nice about this, that if you do this right, it fits nicely on that 6x6 grid. And it does fit great, right? Because we're going to 6, we're going up to 54, which if we go by 10s will be fantastic. And then this goes from 0 to 5.5. If we go by 1s, it's going to be fantastic for that. So let's do a little, we're going to, again, do a little less precise version here than maybe we should. So 1, 2, 3, 4, 5. Whoopsie. And then at 6. And then here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, now we're reminding ourselves about what our x variable is. This is t. This is in seconds. And of course, we're going on that from 0 to 54. So 0, oh, sorry. Don't screw that up. 0, 10, 20, 30, 40, 50, 60.
Yeah, that sent me all the photos of all the work. Not the work, but the pages.
Why do you have to do it on here?
Because they don't have the book.
Right back. Doing some parenting. Come back. All right, I'm back. Sorry about that. Okay, so we've got here on the y-axis ln delta v. So that's going to be biggest value is 6. So 1, 2, 3, 4, 5, 6. And it's ln delta v. Which is a good question. What the bleep for a unit is that? Is it maybe in ln volts? No. I don't know if that even makes sense. Do they have a unit on here? How are they doing this? Shoot, I'm not even sure how to do this. All right. Honestly, I got to think about that. Unit, question mark. Okay, not sure. Okay, I'll get back to that. But let's just take a look at the data. We're going to put the data on here. And we're going to look here, a delta. So this is our x value here. And this is our y value. First one is 6 for the time, which is like here. And then 5.53 is like up here. There we go. Second value, 18 is a little less than this and is at 4.3. 4.3 is like right there, a little to the right. You get the idea. Do a better job than I'm doing here. So next one would be 30 and 3.5. That would be like right there. Next one would be 42, a little bit more there, and then 2.3, which would be like right there. Then we have 54 and 1.79, which will be like here, and 1.79 would be 5, right there. All right, well, that looks actually quite pretty there. I like that actually quite a bit. So let's take a look here then. We can make a straight line fit. Let's use some kind of straight edge that we have available. I have some paper. That's good enough for me. Test here. And we're going to go with a straight line fit through this. Come on. All right, so go right through here. Extend it over here. There we go. There we go. That's the line I get. Looks pretty good to me. And again, if you're using a proper ruler and all that stuff, you can probably get a better value. We can now get our values read off here if we'd like to. We got 5, 6, 6.5 as our y-intercept. So b is equal to 6.5 maybe, something like that. And our slope, we need to find the slope of this line. And for that purpose, I'm going to just take 2 points on the line, and I'm going to take maybe this one right here, and then maybe this one right here. We're going to write these down. So this first point right here is 15 comma 5. So we have 15 comma 5 is our first point, and our second point is 50 comma 1.5. 50 comma 1.5. Okay, and just a reminder, pick 2 points on your line. Do not pick data points. Instead, choose 2 points on your line to find the slope. Once we've done this, we don't want to screw this up. So then the slope is rise over run. We're going to start at 5 and we're dropping down to 1.5. So the rise is minus 3.5 and the run is 35. Well, that's convenient, isn't it? Oh, that's cool. All right, so the slope is minus 0.1. There we go. All right, so the slope is minus 0.1. And of course, that means that we found tau, because tau is equal to minus 1 over the slope, okay, which is minus 1 over minus 0.1, which is equal to 10 seconds. So we found a time constant of 10 seconds. Okay? Makes sense? Too fast, too slow, just right? Good. Okay, excellent. So now they give us the capacitance of the capacitor, and we know, remember, tau is equal to R times C, so that's kid stuff. If they tell us the capacitance, now we can find the resistor simply by saying R is equal to tau divided by capacitance. I'm kind of squeezing it a little bit. Okay, we're still okay. So resistance is tau divided by capacitance, and of course, we can just plug that in. So R is equal to tau, which is 10 seconds, divided by the capacitance, which is 1.5 microfarads. 1.5 times 10 to the minus 6 farads. And you see already, this is going to be a big number, okay? You take 10 seconds, and we divide it by 1.5 times 10 to the minus 6. Two things happen. 10 divided by 1.5, well, that's 6.7, right? 6.6 and 2/3. And then we have dividing by 10 to the minus 6 is times 10 to the 6, or a million. So we're talking about mega ohms here. So we're getting 6.7 mega ohms as our resistance. Okay? Now, everybody okay so far? Okay, and on the solutions, I'm just looking at it. They actually got 12 seconds. That's okay, and they have 8 mega ohms, but that's close enough. Okay, now let's take a look at the last question. We're in part E right now. This is part E1, and then E2 asks. Oh shoot, we erased our. Oh no, wait, here it is. Sorry, here it is. Here's our diagram. Now they're saying, what would happen if the capacitance was greater, but the resistance was the same? Okay, so let's just write that down over here. So we're now going into part E2, not EII, E2. Okay, so we're calm, we're not frightened, that's important. So R same, but we're going to have the capacitance greater, so capacitance is going to go up. If R stays the same and the capacitance goes up, then what's the net effect on tau? Okay, what's the net effect on the time constant? I'm writing in an area you can't see. Isn't that fun? Okay, so up here, I'm writing up here. So for part E, II, or E2, as you guys call it, haha, very funny. So R stays the same, capacitance increases. What happens to tau? Also is greater, exactly. So we are increasing the time constant. Now let's take a look back at what does that mean? Okay, time constant is increasing. Okay, so let's take a look. If tau gets bigger, what happens to m? And this is a little bit of a tricky question. So the magnitude of m, tau goes up, the magnitude of m, what happens to the magnitude of the slope? The magnitude of the slope. Slope is -1 over tau. If now tau increases, the magnitude of the slope up, down, decreases, exactly. So the magnitude of m is becoming smaller. Okay, it's still negative, okay? But now that means that it's negative, but it's shallower. It's not as steep, it's less steep. So instead of going down like this, it wouldn't go like, oopsie, sorry. Instead of moving in this direction, it would now move in this direction. What happens to the y-intercept? There's no change to the y-intercept. It should stay the same. So we should get a line that looks something like this. Like maybe like that. Just as an example. Okay, so this is for a increased C. There we go. And the color would really be helpful. I need to get more markers. So there you go. Okay. Yeah, Amazon, here I come. Okay. Does that make sense? That problem? Where are we on time? 6 minutes to go. Okay, so we got through that pretty quickly. Okay. Is the problem make sense? Okay. Yeah. Okay, good. We're at the end of the week 2 of our self-isolation that we're going through. So it might be good to just reevaluate for a couple minutes where we are right now. We're meeting 4 times a week, Monday, Tuesday, Thursday, Friday, each time 1 period. And my plan is to continue what we're doing in terms of working through about 1 free response a day, maybe getting a little faster, hopefully. I mean, it looked like we were a little quicker today, so we didn't need the whole period. So does that make sense? Should we continue with this process as we're doing it? Or should we do something different with our time in the video chats? Or what do you guys think? Okay. Hannah thinks it's good. How's everybody else voting? Okay. Okay, good. Don't be shy. Yuppers. Agreed. Okay. The other people have either left or are shy about saying they don't like this and would rather be doing something different. No response. Okay. I'm going to take that as let's continue what we're doing. Now, next week is technically the last week before spring break. And then after spring break, better than nothing. Hey, Gio, good to see you, buddy. Okay. All right. And I'm open to constructive suggestions. So if you guys have other suggestions, you can also just email me or WhatsApp me to make a suggestion. Like I like to do something. I didn't want to say anything, but I really could use help. And we can go from there. I also wanted to alert you guys again. I'm keeping sending you guys the College Board live streams they're doing. I think there's some good stuff there. At least Hannah was on yesterday to see Josh Beck, who's, by the way, awesome. Apparently a good job with Torque. There's another presentation today on Torque experimental design, and there's also a live stream on Calculus BC. I think it's BC, that is relevant, I think, to some degree to our work, because they're talking about solving motion problems, and that would be helpful for AP Physics C mechanics. My plan is after. Good question, Ray. I'm not sure yet. I'm still waiting specifically, and this is why we're still waiting on this. Next week, there's supposed to be an announcement regarding the test date for AP exams. I am assuming that the dates will be pushed into the future. Once the dates are pushed into the future, I'm probably going to move the clausur a little bit to not make it the day after spring break, which seems kind of nuts. The day was chosen originally in order for us to be able to take the clausur, get it back to you, and then have you guys take the AP exam just a couple of weeks later. Now, if the exams are pushed into the future, I am assuming they will be like May 20th or so. Okay. But I don't know anything. I don't have any secret information. I just know. Okay. I am working under the assumption. Well, here's two things. Again, prepare for the worst and prepare for the best. I don't know if that made any sense. I'm not sure which one's which. I personally, I don't think we're coming back, but we're scheduled to coming back April 20th in person at school. But I think we're not going to. So but let's make the best of this as much as we can. And then if we go back in school on April 20th, great, then we can do in-person instruction. And if not, then we'll just carry on. And I think we've got a good system working right now. Hey, Ethan, good to see you. We're not sure about the clausur yet. We're going to figure that out once we're next week. Next week, the AP dates will be announced when the actual exams will happen, and then we'll most likely adjust the clausur date appropriately. So have a good weekend. My plan is to see you on Monday at 14:15. So Monday it'll be 14:15, and I'll also keep posting all the other live streams as they become available and are announced. And keep working, keep learning, and see you guys later.